and we're sending about 600 kilotons of scrap overseas every year, which is actually similar to what New Zealand Steel produces domestically.
So let's get into the nuts and bolts of it. Aotearoa New Zealand exports hundreds of thousands of tons of scrap steel every year, and there's a significant opportunity sitting in that. Today, I'm having a kōrero with Michael Allison, whose Cambridge research mapped exactly what that opportunity looks like and what industry can do to capture it. This study explores the future of steel circularity in Aotearoa, New Zealand, and how the industry can reduce emissions through increased recycling, reuse, and improved material recovery. The research looks at structural steel used across the New Zealand construction sector, including both locally manufactured and imported steel products, rather than focusing on any specific manufacturer or product line. Using a combination of scenario modeling, stakeholder surveys, and industry interviews, the study investigates how interventions such as the New Zealand Steel planned electric arc furnace, higher scrap collection rates, structural steel reuse, and renewable electricity and digital material tracking systems could really influence the environmental performance of the wider New Zealand steel industry. Michael, welcome. Michael, tell me a bit about yourself and tell us about the research that you've been conducting with HERA.
Sure. So I am an engineer originally from Christchurch, New Zealand. I head up to Auckland to study after high school, originally studying science and a bit of music, interestingly enough, and then went into civil engineering, where I got passionate about construction management and a range of other types of engineering too, a bit of structural and hydrology and water. And then after graduating, I moved into the construction industry up in Auckland and worked for a commercial construction firm on a range of different projects, from hospitals to schools to mixed-use residential, and rose up the rank from site supervisor, site manager, project manager, etc., and got quite passionate about innovation in construction and how we could revolutionize the ways we do things. But after a couple of years working professionally, I head overseas to Cambridge in the UK to study a master's. The master's was called Phil in Engineering for Sustainable Development. And the idea with this master's is it takes engineers from different backgrounds. Most tend to be civil engineering, but also biomedical engineers, software engineers, mechanical engineers, mechatronics, etc. And it teaches them sustainability frameworks and skills, things like circularity that we'll be talking about a little bit today, and teaches how to apply them in their engineering craft. And while I was studying my master's, I did a dissertation and had help from HERA working and researching steel circularity in New Zealand, which is what we'll be talking about today.
Yeah, and we'll jump right into it as well, right? So when you started mapping the flows through steel within New Zealand's economy, what was the finding that kind of really surprised you?
Sure. So a big part of the research was conducting a material flow analysis. And this was a starting point, I suppose, to get some quantitative data that I'd use for the qualitative aspects of the research later. And I wanted to get a clear picture of steel flows and stocks in New Zealand. And I think some of the numbers themselves that came out of that process were really interesting. So, for example, New Zealand has approximately 52 million tonnes of steel in use in stocks, and 28 million of those are in buildings and infrastructure. And the other 24 million is in other industries such as vehicles, packaging, etc. And if you divide that by the population, that's roughly 10 tonnes per person. So every New Zealander has 10 tonnes of steel, essentially to their name, which hopefully means that steel becomes something important for the wider population. And I think it's pretty cool to be able to put an approximate number on New Zealand steel stock size. And then an important part of the research was using that material flow analysis to estimate our scrap exports. So I knew we exported scrap, but I hadn't appreciated the scale until the numbers came together. And we're sending about 600 kilotons of scrap overseas every year, which is actually similar to what New Zealand Steel produces domestically. And then my goal for the research was to visualize that into a Sankey diagram, which is quite an interesting way to see how those flows and stocks combine together. And you can start to see the inefficiencies and opportunities, things like the mining of iron sand on one end, how we smelt it through coal-based processes to make crude steel. And then on the other end with the scrap steel, how we ship that off to places like Bangladesh, India, Singapore, Australia, for example, to be melted down, often on dirtier grids than ours.
And what does it really cost to even ship those out?
There's two costs, right? There's the carbon cost and the monetary cost. So I was mostly looking at the carbon cost, which I think is quite interesting. So a big part of this research was after working out the material flows, putting emissions factors to each of those. And the idea is we could take 1 kiloton of scrap steel that was exported and work out what was the cost. So one benefit of an electric arc furnace in New Zealand is that scrap steel that used to be exported overseas and melted down elsewhere, we obviously melt down in New Zealand. And some of the savings there come from the renewable aspect of our grid. But a key part that's often overlooked is the transport emissions, which can be relatively significant.
Yeah, and before we jump into New Zealand Steel EAF as well, because New Zealand currently produces it through a very carbon intensive process. And I guess what kind of factors contribute to that because it's higher than the global average?
Sure. So there's a couple of things. First, the iron source. So New Zealand Steel is the only steel plant in the world that uses iron sand as feedstock, which is pretty awesome. So it's an extraordinary piece of engineering history. Glenbrook's been doing it since the mid-1950s, but iron sand does intrinsically require more energy and produces more emissions per ton of iron than other conventional iron ore used with steelmaking processes. And then that brings you to the steelmaking itself. So even though the back end is a basic oxygen furnace, the front end reduction process, what's known as direct reduced iron or DRI, is unusual. So most DRI globally would use natural gas. New Zealand Steel, on the other hand, uses coal and rotary kilns because that's what was economic when the plant was built. And that's what suits the iron sand chemistry. So gas-based DRI runs at something like 1.5 tons of carbon dioxide per ton of steel, whereas coal-based DRI, such as at Glenbrook, is more like 2.5. And then there's a scale component as well. New Zealand Steel produces 600 to 700 kilotons of steel a year, whereas a typical integrated mill in China or India does 5 to 10 million tons. So the smaller scale does mean less efficiency. It means less capacity for upgrades. And the plant is very impressive given what it is, but it was never going to match the per ton efficiency of something like Tata Steel.
Yeah, because you calculated that recycling our scrap steel overseas would produce around 4 times the emissions, because you were mentioning earlier as well, of recycling it domestically, essentially, right? And why do you think that is?
Sure. So we touched on that earlier with the transport question. But EAF steelmaking, or electric arc furnace steelmaking, is essentially an electricity question. So the chemistry is straightforward. You're essentially just melting down scrap steel. What matters is what powers the furnace. So New Zealand's grid is around 80 to 85% renewable, depending on how the hydro dams are going in a given year. And this leads to an emissions factor of about 120 grams of carbon dioxide per kilowatt hour. The countries we send scrap to are running grids that are 5 to 6 to even 7 times more carbon intensive. So as I said earlier, we send scrap to places like Bangladesh and India, and their grids are something like 600 to 700 grams per kilowatt hour. So 6 times higher than New Zealand's. And even Singapore, where we send some scrap steel, which is one of the cleanest destinations, it's about 400 grams per kilowatt hour. So 3 times less efficient than New Zealand. So that same electric arc furnace process, you're producing for the same ton of steel, you're actually emitting much more on those grids than it would be. And as we touched on as well, the transport is another component that people often forget about. So scrap is heavy and fairly low value per ton compared to other things we ship around the world. So that freight cost, as we said, it's the carbon cost, but also the economic cost is relatively significant. And you're shipping it a fairly long way from New Zealand because we happen to be down near Antarctica. So that receiving country may then ship the finished product back to us as well. So you can imagine that it really adds up those emissions. And I did calculate that in the research. So it's about 290 grams per ton of carbon dioxide, 290 grams of carbon dioxide per ton of steel using the New Zealand route, whereas the same overseas on average. So you take a weighted factor per each country would send the scrap steel to is about 740 grams per ton. So about 3 to 4 times as efficient.
Because the thing is, in theory, all of this is great research, right? But I think in order for it to get adopted by industry as well, that's, I think, another big question. And we've got the transition, and we know it's going to significantly reduce our steel production. But what do you feel are the key challenges that need to be addressed for industry to really make that transition into using it?
Sure. And this was a big focus of the research. The technology of an electric arc furnace is complicated, but it's solved in a lot of ways. We understand the technology in terms of what we're doing in New Zealand. The EAF is in motion. We're commissioning it at the moment, and the engineering's fairly well understood. But the challenges are the system around the electric arc furnace that we want to build efficiencies for. So scrap supply is the first challenge and something I did a bit of work on. An electric arc furnace only works if you can feed it consistently high quality scrap. So that means improving on-site sorting at the demolition stage of a project, preventing contamination, building reliable collection infrastructure so you can ship the scrap around the country, and keeping that scrap in New Zealand rather than letting it go to export markets, as we just talked about. And an extension of that is the geographic nature of New Zealand. We have two separate islands. We're a very long country, so having the EAF up in Auckland, it does mean scrap from Christchurch or Dunedin can't easily reach it, just from an economic point of view. So at full ramp up EAF, you're probably looking at the EAF just serving the North Island scrap pool, and the South Island continues to export. I did look at the potential use case of building a mini mill in the South Island, which is a possibility. There were mixed feelings on that from the survey respondents. Or increasing domestic shipping logistics, improving our domestic shipping up the side of the South Island to the North Island might be another solution there. So scrap supply is a really important factor. The other really important one is electricity supply. So the Glenbrook EAF will draw a substantial load, which means the country has to keep on building out our renewable power generation to give the EAF the best clean energy possible. And obviously, if we don't do that, the risk is the EAF's emissions reductions get partially eroded by gas generation backing up in dry hydro years, for example. So scrap supply and electricity factors are two things I varied in my research scenarios. I also did a sensitivity analysis on this, and while both are important, the scrap supply trumps in terms of emissions benefits.
Yeah, because you just touched on scrap collection rates. It's a perfect segue to even ask if you can walk us through why scrap content has such a strong influence on overall emissions, because you've touched on the fact that, yeah, we've already got scrap dealers and all of that, and we need to figure out how we domestically really transport everything as well. But what other influences does it really have?
Sure. So it comes down to where the emissions originate from in steelmaking. So about 80% of emissions from primary steel production come from the chemical reduction of iron ore. So that's taking iron oxide and turning it into metallic iron. And this step requires a reductant, which tends to be carbon from coal, and that carbon ends up becoming carbon dioxide molecules. Regardless of how efficient your process is, it's just the chemistry of steelmaking, you have to release that carbon dioxide. When you use an electric arc furnace to use scrap steel and melt it down, you essentially skip that step entirely. So you already have metallic iron, somebody else did the reduction maybe decades ago, and when you melt that scrap in an electric arc furnace, you're just paying the energy cost of melting, which on a clean grid is very small. Obviously, if you were using coal-based energy to melt down your scrap, that would be less efficient. But the whole point is you don't have the chemistry component of emissions anymore. It's just the energy input to melt it down. And if you've got a clean grid like New Zealand does, that's very efficient. So that's why a ton of electric arc furnace steel made from 100% scrap might emit 0.2 or 0.3 tons of carbon dioxide, while a ton of electric arc furnace steel made from 100% DRI emits 1.4 to 2, which is some of the modeling I did in my research as well. It's all about the scrap aspect of the electric arc furnace. It's not just using the electric arc furnace on virgin steel, it's recycling that scrap that's really important to skip that chemistry step, essentially. So when NZ Steel, they've got an EPD that shows a steep drop in emissions as scrap content rises. That's not necessarily an efficiency gain, that's just avoiding that chemistry. And every percentage point of scrap added is a percentage point of iron ore reduction that doesn't need to happen. And then you touched on the sensitivity analysis. So yeah, finding that scrap collection beats grid improvements. It's the same logic. So New Zealand's grid is already very clean. So if we go from 0.12 kilograms per kilowatt hour of carbon dioxide emissions to zero, that's taking something very small and making it slightly smaller, but improving scrap collection from current rates to near perfect collection adds more scrap root steel into the mix, which displaces more of that DRI root steel, which avoids those chemistry emissions.
And the thing is, because right now steel reuse as well is quite in early stages. Your research targets at least 30% structural steel reuse by 2050. Here's hoping. What do you think is what needs to change for us to really get there? Because research is there, and we've got all the evidence we really need, but industry shift is also what's really required.
So first up, you need a reused steel stockist. Without somewhere to store and recertify reused steel between projects, the supply chain won't function. So in the UK, where they do reuse steel and they do have an existing supply chain, they've got companies like EMR, European Metal Recycling, they have Cleveland Steel, and they show what this looks like in practice, where they've got reused steel stockists who have yards. New Zealand doesn't have one, so that's an obvious gap. Another thing is certification pathways. So right now, if you wanted to use a reused steel beam in a consented building, there's no clear route through the building code. You'd be doing it under alternative solutions, which means the structural engineer carries the liability personally, and that's a fairly grave engineer, obviously. And NZS 3404 needs some sort of defined provision for reusing structural steel. What tests are required, what documentation, what acceptance criteria, etc. And then I guess it's a design culture aspect as well. It's a chicken and egg situation where reusing steel requires the engineer to design around what's available rather than specifying what's needed and asking the mill to produce it. So that's a different way of thinking, and it requires understanding what section availability is out there. There might be a digital catalogue, digital passports, etc. And that's where that comes in as a potential solution too.
Yeah, and that's what I was going to add as well. Like a digital steel passport would just be a lot more beneficial in just understanding where that steel's come from for us to be able to better reuse it as well. Because in most of your surveys, I think one of the biggest barriers was reusing steel and certification as well that you speak to. Because how do you think that would really shift? This is more of a perception of industry question, but still curious to understand how that would really shift as well.
Yeah, so there's a technical challenge for engineers at the moment, as we touched on earlier. So, as I was saying, having NZS 3404, which is the structural steel standard, that's something to begin with. So, that's assuming new steel with mill certification. Mill certs come with the section, the chemistry, the mechanical properties, the traceability to the heat. For reused steel, you have none of that automatically. You have a piece of metal that someone says was an I-beam in a 1985 office building. So the engineer has to establish some sort of equivalence. And in practice, that means sampling and testing the reused sections, such as tensile testing, hardness testing, and this can involve destructive samples from a percentage of pieces or non-destructive testing across the full set.
So there are a couple of things that we've already touched on, but I want to just dive a bit deeper into is that you spoke about kind of certification being one of the barriers as well, right? Now, if a structural engineer wanted to really specify reuse steel on a project, what would that process actually involve?
Essentially, they need to establish equivalence, which is really tricky. They've got to take a lot of their own risk. It's not impossible, but it's very onerous. And that's the reason very few engineers take it on. So essentially, when you get these reuse sections, you need to sample and test them, tensile testing, etc., as we were discussing earlier. And that involves lab time, cost, scheduling risk. And then determining the original specification of the steel that you're reusing is quite tricky. And we did a few interviews with EMR in the UK on this, and they've got a great process in place. They do existing asset surveys, for example, to have this information stored in material passports. But tracing it back to the original mill cert, if it exists, is really challenging. And otherwise, if you can't do that, you need to infer it from the HERA, the manufacturer. And then documenting everything is the tricky part. So in an alternative solution under the building code, because the standard doesn't have a defined pathway. So this means the engineer signs off personally on the equivalence argument. And then you have the building consent challenges. So the council reviewer has to be persuaded that the alternative solution meets the building code performance requirements. Some councils will be very enthusiastic about this, but we have others who might not. And obviously they're stretched as it is. And there's extensive documentation and time involved. So this is another challenge. And you can start to see when you've got all of these complexities, added cost, added time, added risk, why these things don't happen at the moment.
Yeah, I feel like digital steel passports will really solve that problem. So before we go, I've just got two quick questions as well. If the EAF is implemented, New Zealand Steel's EAF is implemented, and no other changes are made, how much of a potential emission reduction can the industry realistically capture?
Roughly half, maybe slightly over half. So the full practical scenario I modeled, which is an electric arc furnace, plus 30% reuse, that optimistic scenario we were talking about earlier, plus 93% scrap collection, which is an improvement from the current 85%, plus a fully renewable grid, that gets you to about 870 kilotons of carbon dioxide reduction per year in the construction sector, which is about 58% of current emissions from the entire steel industry, which is amazing. If you were to just put the EAF alone in and not have those other benefits of improved scrap collection and a better grid and better reuse, you get something like 35 to 40% rather than the 58%. So you're capturing a bit, and it's a good step. And obviously that's where we are right now, or we're about to be, but you're missing out on half of those potential emissions reductions. And you're focusing on a single intervention. And these things can reinforce each other once you implement them and encourage that circular culture. So what you're leaving on the table is fairly significant. That scrap collection component, getting from current rates to near perfect domestic collection, is the next biggest lever. And as we discussed earlier, the grid improvement is smaller, but still meaningful. But what is really important is the grid improvement isn't so much a responsibility of the steel industry, whereas improved scrap collection very much is. So that's something we can all improve.
So the one last question would be for someone who's listening from the industry right now, what is one thing they could really do without waiting for standards, without waiting on the government to make any changes? What's one thing that they themselves could really do?
Sure. The easy one, or easy-ish one, is improving on-site sorting at demolition and construction phases. It sounds small, but it's the single most impactful thing that the industry can do right now without waiting for anything else. On a typical demolition site today, structural steel, reinforcing sheet steel, mixed scrap, that all gets bundled together in skips and they go to a scrap dealer. And then the quality and the traceability are all lost at that point. The scrap will command a lower price. The recycler can't sort it as efficiently. Contamination becomes an issue, and reuse is very much impossible because you haven't actually identified what came from where. So better practice is having separate bins on site, separating your structural sections from your rebar, from your sheet, keeping contamination out of there. And the next step is photographing and recording where the high value sections came from. It costs very little, but makes a big difference for potential reuse in the circular steel economy. And all it takes is a few extra skips and a bit more labor time and potentially a couple of training sessions for the demolition crew. But the economic return is immediate. And then for fabricators and stockists, I guess a great first step is digitizing any mill cert data that you have already. Most fabricators will have PDFs and folders, and converting that to some sort of structured digital format, recording some of the important information, creates the foundation for a material passport system without waiting for one to exist. And obviously that inertia being the first step is really important. And those who do get ahead of it will be advantaged when the requirements arrive. And then I guess for structural engineers, it's about getting familiar with how it's done in other countries. In the UK, reuse is fairly common. There's some great case studies and there's some great guidance as well. So when the first New Zealand project comes up that really pushes for reuse steel, you want to be the engineer who really knows how to handle it, and that puts you in quite a competitive position. And none of these solutions require new standards or a whole lot of funding or new policy from government. It just requires some industry to get involved and make the most of the electric arc furnace we've got and work on those supply chains.
Yeah, I definitely feel like a digital steel passport will add so much benefit to the supply chain, especially with the New Zealand Steel's EAF coming up as well.
Yes,
Thank you
100%.
so much, Michael, for joining us.
Cool. Thank you so much, Salita. Appreciate it.
So there you go. Thanks for joining our conversation with Michael Allison today. If you'd like to connect more with him, you'll find his details in the show notes. And hit subscribe if you liked what you heard today. Please like, review, or share with other metal minds you may know. Let's spread the word.